Well, in continuing our educational journey through hypothesis testing, we're going to look at some different hypothesis tests and different distributions in some cases from what we've been seeing so far. So this next LOS, it says identify and interpret the difference in means test. Now, we've got two samples. They might be independent, but they might be dependent. So we've got one test we're going to use when they're independent, and we've got another one we're going to use when they're dependent. So here's our first one for independent samples. And what have we got for our test statistic? Well, it's going to be a t statistic. And we've got here the difference between the mean of sample 1 and the mean of sample 2. And we're going to reject if that's too far from 0, because our null hypothesis here is that the means of both of these populations are equal. So if we got two sample means that were exactly equal, we're sure as heck not going to reject the null hypothesis of equality of population means. Now, it says identify and interpret here. We don't believe that anybody, except statisticians, remembers these. Okay? Because this is kind of an aside down here. It says, well, this test statistic is calculated differently, depending if we assume the variances of the two populations are equal or if we assume that they're unequal. So it's this denominator that's different. I think what's important to know here, one is that it's a t-test. And when are we going to reject? Well, we're going to reject if that t-stat is greater than or less than the critical values. So clearly, we're not going to reject if the sample means are equal, 0. And if the sample means are not equal, then we have to figure out, well, is that difference statistically significant? So that's what we're getting out of this t statistic here, which is our test statistic, and it follows a t distribution. So it's a t stat, and we're going to reject if it's too far from 0. It's a two-tailed test. I think that's what you should be expected to know about the difference in means test. Now we can go through an example here. We've got abnormal returns from horizontal mergers. Abnormal returns usually means returns in excess, if they're positive, in excess of what you would expect to make on a particular strategy or portfolio in equilibrium. So with horizontal mergers, we've got a mean abnormal return of 1% and a standard deviation of 1%. And then we've got a sample of firms that went through vertical mergers. And their mean abnormal returns are 2.5% with a standard deviation of 2%. So we're going to assume that these samples are independent. And our degrees of freedom are 120. Remember, that's the one thing we need to know for a t distribution is its degrees of freedom. Our significance level is 5%, and we calculated the t statistic as minus 5.474. Determine whether abnormal returns are the same for horizontal and vertical mergers. Well, I'm suspecting they're not. There's our null hypothesis that the difference is 0 versus the alternative hypothesis that the difference is not equal to 0. So our level of significance for a two-tailed test, we see our degrees of freedom there. And we do have a two-tailed test, and we have the 5% significance level. So that's what we want for our critical value, compare our test statistic to. And notice, we've got a pretty good sample size, so that's getting pretty close to the normal critical values of 1.96. But even with 120 degrees of freedom, it's still a little bit wider confidence interval for this t distribution. Well, we're way past 1.98. We're at minus 5.474. So we're going to reject equality. Pretty straightforward. Sounds reasonable as well. Conclude that the mean abnormal returns are different for vertical and horizontal mergers. Shocking, but true. Test statistics. Now, if we have dependent samples, we can't use that previous test. If we have dependent samples, okay, what we're going to do, say we've got two oil companies, and we're looking at their returns, their weekly returns, and we want to know, are they different? Instead of taking the mean for each of them, as we did with the difference in means test, we're going to take for each week, we're going to take the difference between the returns on, say, Conoco and the returns on Royal Dutch Shell, two integrated oil companies. So now, if we say we've got 2 years, 104 weeks worth of data, and so we've got 104 differences. And so that numerator there, this is the hypothesized mean, okay, and this is the mean of the sample differences. Now, for the test of equality, this is simply 0. So, we've got 104 differences, weekly differences in returns. And then we're going to take the average of those. And that average is what turns up right here. So clearly, if that average is 0, we're not going to reject. If that average is too big or too small, we're going to reject the hypothesis that the returns are equal for these two dependent samples. And in the denominator, we've got the standard deviation of the sample differences over the square root of n. So that's a pretty familiar version at this point for us of a t-test. We've got the standard error down there in the denominator, and we've got the difference between the hypothesized value and the average weekly difference in returns in the numerator. If that's big, we're going to reject. If it's really negative, we're going to reject. If it's around 0, we're not going to reject the hypothesis of equality of means for the two populations. So let's walk through an example of this. An analyst is examining estimated betas in an industry before and after deregulation. So those are our two populations, before deregulation and after. Betas may have increased or decreased. The analyst calculates a t statistic of 10.26 based on a sample size of 39, there's n, using a 5% significance level, determine whether there really was a change in betas. So our null hypothesis, difference is 0. The alternative, difference not equal to 0. So now we look at our degrees of freedom and our levels of significance for a two-tailed test. So there's our critical value from the t-table, okay, 2.024. Again, a little bigger than 1.96. So we're going to reject our null hypothesis because 10.26 is way more standard errors away from 0 than we would expect if the null hypothesis that the mean difference was 0 was actually true. So we conclude there is a statistical difference between the betas before and after deregulation. Now we've got another test. So just to sum up, so far we had the difference in means test and the mean differences test. They were both t-tests, and we both were rejected if we were too far away from the hypothesized value. Now this is a test on the variance. Okay. If we have a normal population and we want to test whether the variance equals a specific value, and that's all we've written, sigma sub 0 squared, so that's a particular value for variance, it uses a chi-squared test statistic. That's a distribution we haven't talked about. It's a two-tailed test. And as with a lot of our tests, we're going to reject if we're outside the critical values. And again, it says identify and interpret. Okay? It doesn't say calculate. So anyway, our test statistic here is n minus 1, that's our degrees of freedom, times our sample variance, and we're comparing that to the hypothesized variance. And that's distributed chi-squared with n minus 1 degrees of freedom. And we're going to reject if this is too high or too low compared to our critical values. But now these aren't our critical values from the normal. These are the critical values based on a chi-squared distribution. So let's take a look at an example here of testing the equality of variances. To test whether the variances of two normal populations are equal, this is an F test. Test statistic follows an F distribution. Now that would be a two-tailed test, but it doesn't have to be. We're going to kind of game the test by putting the larger sample variance in the numerator. Now, first off, when are we not going to reject this? Well, if our two sample variances were equal, I'm pretty sure we shouldn't be rejecting the null hypothesis that they're equal. And what would that F statistic be if they were equal? Well, it would be 1. So we're going to reject if we're way above 1. Well, I shouldn't say that. If we're significantly above 1 or significantly below 1. So it's a two-tailed test with the critical values 1 below 1 here, and 1 above 1 over here. Okay. So say we had sample variances of 4 and 3. So we could have 4 over 3, or we could have 3 over 4. And if our test is going to tell us that they're not equal, we want to reject equality, it should do it no matter which one we put there. So 3/4 is going to be less than the critical value. I'll put CV, critical value. And 4 over 3 is going to be greater than the critical value. So by putting the larger sample variance in the numerator, we only have to concern ourselves with this. So although it's a two-tailed test, when you look at the F table in the back of the quant book, you'll find that we only look at the upper critical values. Because if we don't exceed the upper critical value, if we turned it upside down, we wouldn't be below the lower critical value. And our degrees of freedom here are n minus 1 and n minus 2. If you look at that F test, it's going to have degrees of freedom numerator along one axis and degrees of freedom denominator along the other axis. You look where they both come together, and that's the upper critical value. So now let's look at some examples of these tests of variance. For the first one, we've got a standard deviation of monthly returns in a 24-month sample. There's our sample size, is 3.8. At a 5% significance level, we want to test whether the population's standard deviation is significantly different from 4%. Now remember, our test is for the variance, not for the standard deviation. So we're going to have to turn these into variances. And our calculated test statistic is given to us here as 20.76. So this is a test of a single variance. So this is our chi-squared one, right? The one we looked at and we said, okay, variance is equal to a specific variance. It was our sigma squared sub 0. So this is a chi-squared test. It's a two-tailed test. Okay? And our null hypothesis is that the variance equals 0.0016. So what we did is we squared this 4%, right? So we put 0.04 squared, and that's what we used for our hypothesized variance. And the alternative is it's not equal to that. So we're going to reject if we're outside the critical values for the chi-square test statistic. So our level of significance, and we have the probability in the right tail. So we're looking at the upper end of this, okay, because we had a positive value. Okay. Now our critical value here with 23 degrees of freedom is 38.076. Well, our test statistic, we're told, is 20.76, and we can't reject it. It's not larger than that upper critical value. Remember, it's a two-tailed test, so where it says 0.025 right here, that's in the right tail. So we've got our distribution. Well, it's not a normal distribution, but I'll draw it as if it was to illustrate, as if it were to illustrate this. Okay, but we got out here, and our critical value is out here. So we weren't in the reject region, so we cannot reject it. And the reason, we've got 5% significance, but here we've got the probability in the right tail. So 2.5% in the right tail, 2.5% in the right tail, 2.5% in the left tail. So we can't conclude that the population standard deviation is significantly different from 4%. Now, let's take a look at our other variance test. Standard deviation of earnings among 31 textile manufacturers is 430. Standard deviation of earnings, 430. Standard deviation of earnings amongst 41 paper companies is 380. At a 5% significance level, test whether the variance of earnings is significantly different in these two industries if the calculated test statistic is 1.2805. Now, where did that test statistic come from? Well, remember, we need the variances, and we're given the standard deviations here. But this was an F test, or is an F test. And in this F test, we were going to put the higher variance in the numerator so we could just look at the upper critical values of the F statistic. So we got 1.2805. Test comparing the two variances. We want the F test statistic. There's our null hypothesis. The two variances are equal versus the alternative that they're not equal. But the larger variance has degrees of freedom of 30. The smaller variance, degrees of freedom of 40. And there's an excerpt from our F table. So this is the F table for 2.5% in the upper tail. Degrees of freedom for the numerator are in the top row. Degrees of freedom for the denominator are along the left side, or the left margin here. So we're going to match those up based on our degrees of freedom for the larger and the smaller one. Putting the larger one in the numerator, we get degrees of freedom in the numerator of 30, degrees of freedom for the denominator of 40, and our test statistic with 2.5% in the upper tail. So we've got basically a 95% confidence interval, 2.5% in each tail. And our critical value is 1.94. Well, we can't reject because our test statistic, 1.2805, is less than 1.94. So we cannot reject the null hypothesis that the variances of these two populations are equal. Same thing. So lastly, parametric and non-parametric tests. All the tests we've done so far are parametric. We've made assumptions about the distributions and population parameters. We had our t-test, our z-test, our f-test. They're all based on standard deviations, variances, means, all those sorts of parameters of distribution. So all those are parametric tests. There are other tests that are non-parametric tests, and we make few, if any, assumptions about the population distribution. Okay. And we test things other than parameter values. One test that you may run into is what's called a rank correlation test. And say we wanted to determine if the rank, the performance rank of a mutual fund in one period tells us much about its rank in the next period. Well, without using any parameters, what we could do is put them in ranks. Say we rank them 1 through 10. Top 10%, top decile, 10%, down to the bottom 10%. So they get ranks 1 through 10. And then we look at their ranks in the next period. And we rank them again and give them a value 1 through 10, depending on where their ranks were. And then we test for the correlation between their rank in period 1 and their rank in period 2. Well, we could certainly extend this over a number of periods, but we're just looking at, are those ranks correlated with each other? Does knowing this rank in period 1 tell us anything about the rank in period 2 or the rank in period 3? So that's a non-parametric test. And if you're at all curious, most of those tests say no. Okay? Those ranks are not strongly correlated.